Okay, I'm gonna walk you guys through my final project. I chose set, queue, and tree as my three data structures. So to start, I have my welcome page, which gives a brief outline of the different data structures that I'm going to be covering, as well as gives sort of a walkthrough of how the sections are laid out. So to start, we'll cover my queue section. It starts with a brief introduction, and then it gives a description of the queue. Um, like a stack, queue is a linear data structure that is open at both ends and stores items in, first out manner. And we kind of just expand upon what that means and how that works. I give an example, such as Amazon fulfillment warehouse that processes orders and how a queue would be kind of used in that scenario. This is a visual representation of kind of what a queue is, showing how there's a front and a rear and how that relates to the DQ and on queue operations. After the description, we get into the operations of queue, which includes going over the on queue, DQ, and front rear, as this picture provides an example of. We then get into the implementation of a queue. And since there are different ways to implement a queue, I'm focusing on the queue.queue module in my example. And so with that comes the different methods and operations that you can do with that module. And so I give a list of those and kind of a summary of what all of those are used for. And this kind of builds up into next our problem exercises in which we implement some of these methods. This then leads into our basic example problems. I use the example of an amusement park line that holds 24 people. And so with this example, we go over how to create a new queue, how to add people to a queue, get the size, and so just a variety of things. For example, we can check to see if it's full. We can get the contents of our queue as well. So check if there's a specific value inside of our queue. So just going over the basic operations within our basic problem example. Next, I give a advanced problem example. In this example, we go over how to reverse a queue using a stack. So I even mentioned up above that this problem example would include prior knowledge of a stack and list data structures in order to implement that. So this just kind of focuses more on building a function that can work with a queue. Lastly, I end with a list of practice problems for the viewer to do themselves. And so I have 12 different activities, each kind of progressing from a simpler to a more advanced implementation of queues. So we'll start with create a queue, print the sizes, remove an element, add more, check if it's full. And then, we get into create a function that performs a simple mathematical operation on the queue value and then removes the item from a queue. So, it's mainly just focusing on the remove part of it, but but we add the complexity of creating a function and performing something else. So kind of using the simple remove method into a more practical scenario. And so we also have create a function that holds a new item to queue when space is available. Starting off simple and then moving to a little bit more advanced. So next we have the set. And again, just gives a brief introduction about what this page covers in a description. So sets are used to store multiple items in a single variable. And it is one of the built-in data structures. I then go over the characteristics of a set, which are unordered, unchangeable, unindexed, and do not allow duplicates. and then I sort of expand on what those means. We then move into the operations of set, and I cover things such as how to access an item, how to set items, remove items, and I give the method and an example of that implementing that method into Python. And so there are a lot of methods I cover, all of which I believe I give a pretty good definition of what those are, and then how they would be used, such as, if you want to keep all the items but exclude the duplicates, you can use the symmetric difference update method, and then I give that example in Python, and then, give a counterexample of the symmetric difference. So, and then I briefly list some other methods. And then I like this visual representation, because I think it gives the viewer kind of idea of what these different operations mean in terms when you're trying to work with two different sets. So then we get into the basic example problems, such as checking to see if an item is in the set, using the update method, remove method. So just kind of going over those basic operations. And then we get into the intermediate example problems, focused on working with multiple sets, finding the differences, creating new sets based off of the available data. And then again, we finish with our problems to solve. And again, it starts with a more basic problem, such as creating a set, adding items and whatnot, and then getting into a little bit more advanced things, such as creating a new set that holds the duplicate items from each set, which is something that was covered, and then creating a function that pops an item from each set and compares them to see if they are the same. So all of these problems can be solved using the definitions and examples that I provided on the page. So then finally, we have our tree section. And again, I give a basic introduction, noting that the tree non-linear data structure, and so it's a bit different. I give a brief description, pointing out its features such as nodes, pointers, and having a parent and child node. I then get into the terminology associated with a tree, such as the root and parent child nodes, subtrees, depths, heights, I then have this graphic example to help illustrate what these terms visually mean. And so in my implementation section, I simply explain that a tree can be built from different ways, but the most common way of building a tree is through a class. And so I simply give the example of how to create a tree node class. The basic example problems cover how to expand the tree class, such as adding a method that prints the items, or to check to see if the tree is full or if there is a node that is empty. We then continue with more advanced methods by adding a method to check the height, ones that traverse the tree and returns the values in forward or reversed order. We then go over how to insert a value into the tree. And we also have an example of how to check to see if the tree contains an item. And then again, we then end with a list of problems for the user to go through. Again, we start simple, such as making sure to understand how to create and add items to a tree. And then we focus on expanding that tree class to include methods that will be of value, such as ones that return the smallest value to check to see if there is a leaf node and remove it, return a value that's closest from a given target value, and even some more advanced stuff, such as transferring data from either a list or a dictionary or a JSON file into a binary search tree object. For the tree section, I have a tree class file completely built, since we kind of go over these in sections in the lesson plan here. It's nice to have an actual built class with all of these methods built together. It's modeled after the example one we had in class, but obviously I've expanded upon it And so that pretty much concludes an overview of my final project.